So final talk session from Sadegh, and he's going to talk about secure stable matching.
Thank you for the introduction. The good news is it's the last talk of this session, so we can take a break afterward. Today I'm going to talk about our recent findings on how to perform secure stable matching at real-world scales. This is a joint work with my advisor, Professor Kushanfar, and Professor Sadegh and Schneider from TU Darmstadt. Dr. Sonwar is also an alumni from our group who currently works in Google. This is the outline of my presentation. First, I'm going to talk about what is a stable matching, followed by a visual example. Then I will talk about why we need privacy in this task. Then I will talk about Yale's garbled circuit protocol, which we have utilized in our solution. The majority of my talk is dedicated to our two main contributions. The first one is sublinear size circuit, and the next one is early termination technique. I will compare the complexity of our computation with pair work, and we have done extensive experimental results, which I will provide at the end. So a stable matching is the process of assigning the members of two groups to each other one by one, where each person has a preference list. This preference list shows how a person values each person of the other group. The assignment should satisfy one condition, and that's the assignment, there should be no pair such that they prefer each other over than they already assigned partners. Stable matching is used in many applications, for example, in National Residency Matching Program, where a group of medical students are matched to residency programs. Stable matching is also used in capital markets to assign consumers and suppliers. So it's more fun to describe stable matching in the context of marriage. So on the left-hand side, you have a group of boys, and on the right-hand side, you have a group of girls. Of course, each person has a preference list. So if we assign the member of these two groups to each other in this order, this is not a stable match because of this link. As you can see, Alice prefers Ryan over Jack, her already assigned partner, based on the preference list. And also Ryan prefers Alice over Sarah, his currently assigned partner. So this is not a stable match. However, if you assign them in this order, there is no such pair that violates the condition, and therefore it's a true stable match. In the secure stable match setting, we want to perform a stable matching without revealing each party's preferences to any other party. So why is it important? There are multiple answers to that. First, there are multiple studies that show that if an individual knows the preferences of other people, he or she can manipulate the outcome in her favor by changing his own preference list. Second, in some scenarios, the data is confidential by law, so we need to respect that. And the third reason is that, of course, privacy. No one likes to feel he or she wasn't the first choice. We have used Yale's garbled circuit protocol. The GC protocol is a classic two-party secure function evaluation method introduced by Andrew Yao in 1986. At a very high level, GC emulates a trusted third party to which two parties can give their inputs and receive the result. However, this is just a conceptual description, and in reality, there is no third party, and the protocol is run between two parties only. A very simplified explanation of the GC protocol is as follows. It has three main phases. In the first phase, Bob has to describe the functionality as a Boolean circuit with two input gates. So here the functionality would be the stable matching algorithm. Next, he will assign random keys to each wire in the circuit, and for each gate, he encrypts the output wire using input wire keys and forms garbled tables. In the second phase, Alice receives all garbled tables together with the keys corresponding to her input. And in the third phase, Alice starts decrypting each gate one by one until she reaches that true output result of the computation. Random access is a very costly operation in GC because at the same time we need to hide the access pattern, the address, and the data. The basic solution is to put a multiplexer inside the circuit that accesses each flip-flop. And the control signal of the mux would be the address, the output would be the data that we want. But since in GC we cannot escape garbling and evaluating any gate, the access cost for single access is linear in terms of the number of gates or simply the memory size, which is very costly. A more complex but more efficient solution is oblivious RAM, which has, the best ones has logarithmic access complexity. But due to the high initialization cost of the ORM, it doesn't outperform MUX up to a certain point. So this is memory size and this is the access cost. This is the global flow of our end-to-end system. It starts with describing the functionality as a Boolean circuit. So we have written the stable matching algorithm in Verilog, a hardware description language. Then we have fed that into a hardware synthesis tool to get the net list. Then we topologically sort the net list to avoid any deadlocks. And at the end, we have a sorted net list of the function. This is an input to the GC protocol that is run by two servers, one acting as garbler and one acting as evaluator. These messages here are offline, and they have to be performed only once. And these building blocks here are the description of the GC protocol that I discussed before: garbling, communication, evaluating, and merging the result. So each party that wants to participate in the stable matching has to send two different encryptions, which is XOR share of their input preference list, to two servers. Then two servers run the GC protocol using this sorted net list. And at the end, they merge the result to output the stable match list. Gale-Shapley is an algorithm for finding the stable match. As you can see, it's an iterative algorithm, and at each iteration, a free man who is not already assigned to any partner, what's so-called proposes to a woman that he prefers the most, but he has not yet proposed to. And the algorithm continues until the match list is stable. In the worst case scenario, we need to run this loop for n squared. It has the n squared complexity. But here, finding a free man is not trivial in the GC protocol because we need to linearly scan all the men's lists to find a free one. So here we have a specific module in the circuit to perform this task, which I'll describe later. As I mentioned, the worst case scenario for the algorithm is n squared. But due to the invalid proposals that we have in the GC protocol, we actually have even worse than mathematical worst case of the algorithm when run in the GC protocol. We have also done some statistical analysis on the average number of proposals. And as you can see, it scales linearly instead of n squared with the number of participants or set size. This is the schematic view of our sublinear size circuit. The sublinearity is with respect to the number of participants in each group. I'll describe each building block in more detail. So this submodule acts as a control flow of the whole circuit, and it basically implements the majority of the code in the stable matching algorithm. This circuit finds the free man in the previous clock cycle and feed it to the ACC, algorithm combinational circuit. And this part of the circuit is memory, which can be implemented either as MUX or ORM. And as I talked before, in order to avoid invalid proposals, we have introduced a technique which is called early termination that finds whether a list is stable or not. Because in regular execution, everything in the GC protocol is garbled, so you cannot really tell if the match list is stable at this time or not. But using this protocol, we can reveal one bit of information at each clock cycle and see if the match is stable or not. Of course, this is not free. It comes at the cost of revealing the total number of proposals needed to reach a stable match. And it's an optional module that we can use or avoid. So ETT can be used in any iterative-based algorithms. For example, it's used in Calctopia, which is a secure spreadsheet company, and they have used our technique in their security product as they have announced in the security model. So depending on which type of ORM you use in the circuit, you get different complexities. The vertical bar shows different kind of ORMs, and the horizontal bar shows different variants of stable matching. We have linear ORM, which is basically using MUX, square root ORM, and circuit ORM. And for the horizontal bar, we have general stable matching plus ETT, early termination technique, and limited stable matching. The limited stable matching is when the preference list for each person is limited to a constant number like 20, whereas we can have like 1,000 people in each set size. And as you can see, linear ORM is better up to a certain point than both ORMs, after which a square root ORM comes in and outperforms MUX up to a certain point, which is around 4,000 people. And after that, circuit ORM outperforms all of those solutions. Here is a complexity comparison with prior work. The first solution had the total computation complexity and communication with n to power 5, which is very huge. During time, it's reduced down to n squared like 3. As you can see, our work together with Keller et al. Solution have the best asymptotic complexity. It's important to note that the majority of operation in our solution is symmetric key encryptions, whereas the initial solutions are public key-based, which are far more expensive. So here's the experimental results for different set sizes and different ORM schemes. The upper table shows the result for regular execution. The down table shows the result when using early termination. For experiments that took more than a few hours, we use our cost function to get the result. I know these numbers may sound astronomical, but this is due to the hardness of this problem. For example, comparing to Keller et al. Solution for set size of 8,000 people, they report 10 to power 12 seconds execution time estimated, so which is equivalent to 47,000 years. But we need slightly more than a day to compute this functionality. Comparing to the original paper for square root ORM, they have 33 hours execution time for set size of 512, same scenario, where we have 8 hours of execution time without using ETT, and slightly, close to 5 minutes execution time when using ETT. Concurrent work that was published in CCS 2016, they introduced oblivious linked list, and they report 48 minutes execution time for same set size and scenario, which is less than our regular execution, but more than our execution with ETT. So in conclusion, we have studied the problem of secure stable matching, and in particular, we have introduced a sublinear size circuit for this task for the first time. And also we have introduced early termination technique, which can significantly reduce the execution time of the GC protocol for any iterative-based algorithms, and has already been adopted in security products. Thank you very much, and I'm happy to answer any questions.